We're already done with the three types of sight distances. We have done discussing stopping sight distance, decision sight distance, intersection sight distance, and now for Unit 6 of your Module 3, still on the geometric design of highways and railroads, we will be talking about passing sight distance. And in this unit, you will have the following learning outcomes. So, for this unit, we are to determine the passing sight distance required for overtaking vehicles. So on most two-way highways, vehicles frequently overtake slower moving vehicles by using the lane meant for the opposing traffic. So in this image, you see here, you have a truck and you have here a car. So this is a two-way highways, meaning there is one lane for northbound and one lane southbound. So for this one, uh, the the truck is moving at a slower rate or slower speed compared with the speed of your car. So for the car to be able to um, move freely, he will be overtaking this truck. And to do that, he needs an available passing sight distance because he will be taking over or using this lane that is meant for the opposing traffic, opposing their direction, and he needs to do the passing before another vehicle that will use this lane, that originally is designed for this lane, will be able to will pass or will be uh, met by this overtaking vehicle. Passing maneuvers in which faster vehicles move ahead of slower vehicles must be accomplished on lanes regularly used by opposing traffic. So we normally see this in some action movies that involves cars. Ashta states that if passing is to be accomplished without interfering with an opposing vehicle, the passing driver should be able to see a sufficient distance ahead. This time, this is called your passing sight distance, clear of traffic, so that passing driver can decide whether to initiate and to complete the passing maneuver without cutting off the passed vehicle. This is the passed vehicle before meeting an opposing vehicle that appears during the maneuver. So that is self-explanatory. Similar in this picture, the green car here will overtake or pass the slower moving truck in this case. So there is a sufficient passing sight distance that should be available for the passing vehicle to be able to do the maneuver safely. So if you'll notice the red arrow here, if the car will cut in early, then it will have a great possibility that it will collide or bump with the front of the truck. When appropriate, the driver can return to the right lane without completing the pass if he or she sees opposing vehicles is too close when the maneuver is only partially completed. So let's say, for example, you have another car here that is moving opposite the direction of the truck and the green car here. And by the time that this green car is in the same speed and in the same position with the truck, but then it is in the opposite lane, and there is another red car, for example, here that it will meet, and the driver has assessed that it will not, the driver of the green car has assessed that it will not be able to finish the maneuver or the passing maneuver, then he has an option to slow down and go back to his original lane and again try another attempt for passing the truck. Many passing maneuvers are accomplished without the driver being able to see any potentially conflicting vehicle at the beginning of the maneuver. Of course, there are instances that there is no opposing vehicles, making it possible for the driver of the passing vehicle to be able to accomplish the maneuver easily. An alternative to providing passing sight distance is found on section 3.4.4 under passing lanes. This is of course in the provisions given by the 2011 edition of Green Book. Minimum passing sight distances for use in design are based on the minimum sight distances presented in the MUTCD or the Manual on Uniform Traffic Control Devices as warrants for no passing zones on two-lane highways. So, once there are some sections of our roads that passing is not allowed, this is very common in roads with sharp curves. So, there are road signs in the pavement that is placed indicating that there is no that passing or overtaking is not allowed in that road section. Design practice should be most effective when it anticipates the traffic controls, that is passing and no passing zone markings, as I've discussed a while ago, that will be placed on the highways. The potential for conflicts is passing operations on two-lane highways is ultimately determined by the judgments of drivers that initiate and complete passing maneuvers in response to number 1, the driver's view of the road ahead as provided by available passing sight distance. Number 2 is the passing and no passing zone markings. And as similar to the other sight distances, the driver behavior is really an important factor in determining this passing sight distance, these sight distances. And it is also not dependent on the provision of these sight distances that we will guarantee 100% that there will be no failure in or accident that will be met by these drivers, because it is always depending on the behavior of the driver. Okay? Recent research has shown that the MUTCD passing sight distance criteria result in two-lane highways that experience very few crashes related to passing maneuvers. Passing sight distance, when we define it, is determined on the basis that the driver vehicle or the driver wishes to pass a single vehicle, although multiple vehicle passing is permissible. So for the design or the computation of passing sight distance, we normally compute it for overtaking or passing only one vehicle. But of course, in actual conditions, it may pass through or overtake multiple vehicle. It is permissible. The design values for passing sight distances are presented in Table 3-4 and are shown in comparison to stopping sight distance criteria in Figure 3-1. Later we will show 3-1, comparison of SSD and PSD, considering the same design speeds. It is apparent from the comparison in Figure 3-1 that more sight distance is needed to accommodate passing maneuvers on a two-lane highway than for stopping sight distance that is provided continuously along the highway. Again, stopping sight distance is continuously provided along the highway. I have also discussed this on your Unit 5 of Module 3 in intersection sight distance. So here is the comparison of design values, design speeds for passing sight distances and stopping sight distances. PSD is for passing sight distance and SSD is for stopping sight distances. So the x-axis here is the sight distance. So you can see it is really considering the same each of these design speeds. We can say that the PSD or the passing sight distance is really higher in value as compared with the SSD. Research has verified that the passing sight distance values in Table 3-4 are consistent with field observation of passing maneuvers. According to this study by Hardwood and his colleagues, This research used two theoretical models for the sight distance needs of passing drivers. Both models were based on the assumption that a passing driver will abort the passing maneuver and return to his or her normal lane behind the passed vehicle if a potentially conflicting vehicle comes into view before reaching a critical position in the passing maneuver beyond which the passing driver is committed to complete the maneuver. Okay, so similar to what I have discussed earlier in this video. According to this study, Glennon model assumes that the critical position occurs where the passing sight distance to maneuver is equal to the sight distance needed to complete or abort the maneuver. So we can see here the elements of passing sight distance from the AASHTO Green Book 2001 because I cannot find this image in the Green Book 2011, so I just placed this one here. So there are 4 parts of the maneuver: D1, D2, D3, and D4. Later we will go in detail on these parts, and it is further divided into the first phase and the second phase of the passing maneuver. Another study from Hassan and colleagues. The Hassan et al. Model assumes that the critical position occurs where the passing sight distances to complete or abort the maneuver are equal or where the passing and passed vehicles are abreast, whichever occurs first. When we say abreast, meaning the passing vehicle and the passed vehicle are together. In this image, this is the passing vehicle because it is the one that will overtake. And this portion here, this one is the passed vehicle because that is the one that is being overtaken by the passing vehicle. And at point A here, during this time, these two vehicles are abreast, meaning they are side by side. Okay? So the minimum passing sight distances for design of two-lane highways incorporate certain assumptions about driver behavior. Again, driver behavior is different. They are varying. So for example, if a sports car racer is will be doing a passing maneuver compared to a non-professional driver, they will have different capabilities. They will have different judgment. It will be that race car driver will have a lesser amount of passing sight distance that is required. But then in the design, as what I have been telling you in this module, is that we are considering not this outlier values, but then we are considering the average or not the average actually. We are considering the driver behavior criteria or characteristics that will fit the majority of our drivers, because these roads will be utilized by motorists or drivers. Of course, we need to cater to their needs, to their abilities. Actual driver behavior in passing maneuvers varies widely. To accommodate these variations in driver behavior, the design criteria for passing sight distance should accommodate the behavior of a high percentage of drivers rather than just the average driver. Okay? We are considering the high percentage or the high percentile. That is why we are taking the 90th, 85th to 90th percentile every time we consider design values. The assumptions made in applying the Glennon and Hassan et al. Models are: first, the speeds of the passing and opposing vehicles are equal and represent the design speed of the highway. So the passing and the opposing vehicle, as shown in this figure here, this is the passing vehicle, this is the passed vehicle, and this is the opposing vehicle. The assumption is that the passing vehicle and the opposing vehicle operates under the design speed of that certain road section. It's just that the passed vehicle or the vehicle that is being overtaken is traveling at a lower speed. That is why there is a need to overtake. The passed vehicle travels at uniform speed, and speed differential between the passing and passed vehicles is 19 kph. So the passed vehicle is not accelerating, it travels at uniform speed. The passing vehicle has sufficient acceleration capability to reach the specified speed differential relative to the passed vehicle by the time it reaches the critical position, which generally occurs about 40% of the way through the passing maneuver. So at about 40% of the way to the passing maneuver, in the image a while ago that I've shown you, that is a distance d sub 2, about 40% of that distance from the start, the the passing vehicle has already acquired its acceleration to reach required acceleration to reach the specified speed differential. Fourth, the lengths of the passing and passed vehicles are 5.8 meters as shown for the PC design vehicle in section 2 dash. So that 2.1.1, the passing driver perception reaction time in deciding to abort passing vehicle is 1 second. Okay, so it's really a short time for the perception reaction for the driver to decide on to continue or to abort the passing maneuver. If a passing maneuver is aborted, the passing vehicle will use a deceleration rate of 3.4 meter per second squared. Okay? If the uh, driver of the passing vehicle decides to abort the operation or the maneuver, he will decelerate at 3.4 meter per second squared. The same with the one we use in stopping sight distance. For a completed or aborted pass, the space headway between the passing and the passed vehicle is 1 second. And last, the minimum clearance between the passing and the post vehicles at the point at which the passing vehicle returns to its normal lane is 1 second. So let's consider this scenario. We have here blue, the police car here. This is what will be our passing vehicle. We have here the red vehicle, which is the pass vehicle, and we have the yellow vehicle here, or the yellow car, which is the opposing vehicle. So this is a 4-lane highway. So they are divided by these yellow lines, meaning they don't have that much of an adjustment to make in overtaking because they have their separate highways. This police car will not bump into the red car, and this opposing car will not bump into the police car or into the red car. So if we will take a look at the space-time plot of their speeds, the red line here represents the red car traveling at 18 kph, for example, and the yellow car represents here, the yellow line represents the plot of the space-time scenarios of the yellow car. It is also traveling at 18 kph. That is the assumption. Okay. And you have the police car, which travels at a higher speed at 36 km per hour. It is represented by this steeper slope, meaning it has reached this speed, or it has traversed this distance at a relatively smaller time interval as compared with the distances taken by this red and yellow space-time line. So this animation shows it again there. Okay, we can see that the police car is traveling faster. Okay, last. Okay, now let us consider this scenario. What if they are traveling in a single highway? If you will notice, if these two are traveling at 18 kph and the police car is traveling at 36 kph. If they will continue to move, if the blue car will continue to move at its speed without decreasing its speed, then it will bump into this red car. But the option here is to pass through this vehicle or by doing the passing maneuver. So the red one here is the space-time consideration for the red car traveling at constant speed, 18 kph, and for the yellow car is the same. So this broken line here, blue broken line, is the initial, because the blue car is traveling at 36 kph, right? So that is the initial or the ideal in our, similar to what we did in the 4-lane highway. But for this one, because he will be using a traverse or passing maneuver, then he will start at the blue police car original speed of 36 kph. And by that time, when it will come near here, it will follow the red car with the same speed, 18 kph, for it to not bump this car. And then he will decide to continue with the passing maneuver. Of course, it with a higher with an acceleration. It should have a higher speed to complete the passing maneuver. And he will switch lane going here and then going to the other side. And after that one, it will continue with its original speed of 36 kph. So it is shown here in this animation. I don't know if you saw that. That is the what happens in passing distances. Okay, now let's try to separate the different scenarios that is happening in this instance. So let's start with this one. Still, we have the distance time graph here shown. And we have your red car traveling at constant speed, 18 kph, and the yellow car speed, still constant at 18 kph. And we have the original or the traverse. If the blue car or the police car will not be able to, will not change its distance, or it will, if it will not change its speed. But then since they are in a 2-lane highway, there is a need for a passing maneuver. For example, let's think of a scenario that the police car has an operation. He will be going to rescue a certain hostage. That's why he is traveling at that speed. So the first part would be the blue police car with an original speed at 36 kph. So from the original point up to that portion, and then he will, at a certain time, he will follow the red car at 18 kph with that speed. And from that portion, from the end of the police car, from the end of his speed of originally at 36 kph, up to the time that he follows the red car at 18 kph, that is what we call our D sub 1. Next is this portion. The car will now continue with the passing maneuver, and at this point, they will be abreast. The passing vehicle, the blue police car, and the pass vehicle, which is the red car, are abreast. And continuing with the passing maneuver, it has now overtaken the red car without bumping into the yellow car here. And that distance, or the acceleration and the switching of lane and passing maneuver, will be called RD sub 2. Okay, remember that our first phase starts with D sub 1 plus 1/3 of D sub 2, and 2/3 of D sub 2 already belongs to the second phase of the passing maneuver. And next scenario will be the continuation of the blue car at 36 kph. And we call this distance. By the time that the driver was able to finish its D sub 2, by the time that he was able to continue or move into or reverted back into its original lane, the distance from its uh, front and the front of the opposing vehicle is what we call our D sub 3. And D sub 4 is the distance from this distance from of the opposing vehicle by the time that the opposing vehicle and the opposed vehicle, or the rather the passing vehicle and the passed vehicle are abreast. During that time, you will start with the measuring of your G sub 4 up to the time that the car or the passing vehicle was able to complete his maneuver. Okay, his passing maneuver and switch back to its original lane. So that is what we call our G sub 4. And the passing sight distance that is required for these certain types of maneuvers is determined by these distances. So PSD, or the passing sight distance, is just the sum of D sub 1 plus D sub 2 plus D sub 3 plus D sub 4. So as shown here in this image from Ashto Green Book 2001. So D sub 1 is the distance traveled during perception and reaction time during the initial acceleration to the point of encroachment on the left lane, shown here in the image for the first phase. It is often called the initial maneuver distance. D sub 2 is the distance traveled while the passing vehicle occupies the left lane. So by the time that this passing vehicle will start to move to the second lane, up to the time that it returns to its original lane is what we call D sub 2. D sub 3 is the distance between the passing vehicle at the end of its maneuver and the opposing vehicle, or the clearance, shown here. And D sub 4 is the distance traveled by an opposing vehicle for 2/3 of the time the passing vehicle occupies the left lane. So it is the distance traveled by the opposing vehicle. So we consider the opposing vehicle, and it will start measuring it from by the time that the passing vehicle has occupied its 2/3 of D sub 2. So that time will start from this one at point A. During this scenario, when the passing vehicle and the passed vehicle are abreast, you will start with the computation of D sub 4, as I have mentioned a while ago, up to a certain point in which D sub 3 ends. Okay? This is usually denoted as D sub 4 is equal to 2/3 of D sub 2. So here is the different considerations in these values, and you will have your total, which is the passing sight distance. So PSD is equal to D sub 1 plus D sub 2 plus D sub 3 plus D sub 4. We have a formula for D sub 1 or D sub 1, that is D sub 1 times V minus M plus AT1 over 2. We'll take a look at this one and define the values of these parameters. D sub 2 is V times T2. D sub 3 is varying from 100 to 300 feet, so it's up to the designer. And D sub 4 is 2/3 of D sub 2. So D sub 1 is the time of the initial maneuver. This is the time required to finish D sub 1. D sub 2 is time passing vehicle occupies. the left lane. This will be given in the problem. V is the average speed of the passing vehicle, and M is the difference in speed of past vehicle and passing vehicle. So for the example problem here, we need to compute the passing sight distance for the following data. Passing vehicle speed is 96 kph. Overtaken vehicle speed or the past vehicle speed is 88 kph. Time of initial maneuver or T sub 1 is 4.3 seconds. Average acceleration 2.37 kph per second. Time of passing vehicle occupies the left lane is 10.4 seconds. And the distance between the passing vehicle at the end of its maneuver and the opposing vehicle is 76 meters. So let's try to compute this one. Let's start with the passing vehicle. I want to have the passing sight distance in terms of meters. This is equal to d sub 4. And now we have your passing vehicle speed. I want to call this as V. Okay, that is V. If you will go back to this portion, that is V, the average speed of the passing vehicle. Okay, so that would be 96 kilometer per hour. For 1 hour, there is 3,600 seconds. And for every kilometer, there is 1,000 of a meter. Cancelling these units, we will have your velocity in terms of meters per second. So 96 times 1,000 divided by 3,600 is equal to 26.67 meter per second. So I want to use 3 decimal places. And the overtaken vehicle speed, let's just call this one V sub past. So this is 88 kilometers per hour. To convert this into meters per second, this will be equal to 24.44 meter per second. Time of initial maneuver, this is equal to T sub 1. This is equal to 4.3 seconds. Average acceleration is equal to 2.37 kilometer per hour per second. Let's try to convert this one. So 1 kilometer or 1,000 meter is equal to 1,000 or 1 kilometer. And again, 1 hour is equal to 3,600 seconds. And you will have your acceleration in terms of meter per second squared, because we will cancel this 1 kilometer, we will cancel r. We are left with meter per second squared. This will be 2.37 times 1,000 divided by 3,600. This is equal to 0.658 meter per second squared. And we can compute for m, which is the difference between the the speed of the passed vehicle and the passing vehicle. That would be from this formula. Okay, so continuing, we have your m, which is the difference in the speeds v and v pass. So I'll call this v minus vp. This would be 26.667 minus 24.444. 7 minus 24.444. This will be equal to 2.233 rather meters per second. And what else do we have here? We have the time passing vehicle occupies the left lane. This is 3 sub 2. This is 10.40 seconds. And we have the distance between the passing vehicle at the end of its maneuver and the opposing vehicle. This will automatically be d sub 3. That is at 76 meters. Okay. So continuing in our discussion or in our computation, we will now be able to compute for the value of d sub 1. D sub 1 is equal to d sub 1 multiplied by v minus m plus a d sub 1 over 2. So this will be 4.3 multiplied by 26.667 minus 2.223 plus 0.658 times 4.3 divided by 2. And using my calculator, that would be 4.3, 26.667 minus 2.223 plus 0.658 times 4.3 divided by 2. And this will now be equal to 111.192 meter. D sub 2 is just equal to v times t sub 2. And this is equal to 26.667 multiplied by 10.40. And this is now equal to 277.336 meters, or let's just say 337. We have your d sub 3. It was given as 76 meters, and we have your d sub 4, which is equal to 2/3 of d sub 2. And this should be equal to 2/3 of 277.337. 2/3 This is equal to 184.89 meter. So PSD, the passing side distance, let me use another color for this one so it can be easily seen. Let's use blue. So PSD is equal to 111.192 plus 277.337 plus 76 plus 184.891. We have your passing side distance equal to 1.192, 277.337, 76 plus 184.891, and this should be equal to 649.42 meters. It's high really, because if you will notice, the speeds of these vehicles are at 96 kilometers per hour. So they are, I think they are race cars in this case. Okay, so as a review, passing sight distance is determined on the basis that a driver wishes to pass a single vehicle, although multiple vehicle passing is permissible. So this ends the discussion for the passing sight distance. I'll see you next in the next discussion of the horizontal alignment, vertical alignment, and super elevation on the geometric design of roads and highways. Thank you.